Howdy, this is Mr. Potter. In our last episode, we talked about L'Hopital's rule and how that allows us to find the limits for functions when I have something called indeterminate form. And so what I wanted to talk about today is I wanted to talk about what I actually mean by indeterminate. And the key form that we were talking about is whenever we were looking at a limit as x approaches some value of a of f of x over g of x, when the act of substitution gives me 0 over 0. So the question is, why is 0 over 0 considered indeterminate form? Well, the reason is there are several ways that I could try and approach determining what that value is. For example, if I was to look at the line y equals 0 over x, I know that 0 divided by any integer or any real number should give me 0, because 0 divided into any number of parts gives me 0. So approaching it from this venue, I should have a constant value of 0. But I also know that if I'm dealing with y equals a over a, any number over itself should be 1, because the terms would divide out. And so I could say that I'm traveling along this path to get to 0 over 0, in which case I should have a constant value of 0, or I'm traveling along this path to get to 0 over 0, in which case the value should be 1. And I could also just as well take a look at anything over 0, because I know anything over 0 is undefined. This is going to give me either a positive or negative infinity depending on the value of a, and therefore I should get an undefined value. And what we saw in our last episode was that these values could really be any real number, any value between and including negative infinity and positive infinity is an acceptable limit, depending on the functions that we're dealing with. So this really is truly indeterminate, and that's why we need these alternative methods. And of course, the methods we talked about in the past, we talked about factoring, we talked about using a graph or using a table, but we've also introduced this L'Hopital's rule to try and deal with these indeterminate forms. And this kind of begs the question, what are some other indeterminate forms? Because 0 over 0 is not the only indeterminate form, and it turns out that 0 over 0 is not the only situation where L'Hopital's rule is a helpful tool. Some other indeterminate forms are when my limit tends to be infinity over infinity. Anytime that I end up with an infinite function over an infinite function. And I'll see this a lot when I'm dealing with as limits approach infinity or as limits approach negative infinity. I also have the situation where I have 0 times infinity. And also if I'm dealing with the situation of infinity minus infinity, where if I take in the difference of two functions and they're really both of them are increasing without bound. Now, all three of these situations could give me a limit of 0 or a limit of a constant value or a limit of undefined, infinity or positive infinity or negative infinity. So all of these are what we call indeterminate forms. And so I wanted to talk about these indeterminate forms. I wanted to go through a couple of examples. So I'm going to start by going over an example of this infinite over infinite. So let's take a look at the limits as x approaches infinity of 3x squared plus 6x over 2x squared minus 5. Now I'm looking at this, and of course the first thing I'm thinking when I look at this is that I'm approaching it from a pre-calculus standpoint. I see that the degree of the numerator and denominator are the same, and so I'm looking at the coefficients of my largest degree term, and I should end up with a limit of 3 halves. And that will end up being our answer as we evaluate this. But I do want to take a look at it from the standpoint of L'Hopital's rule. If I was to substitute infinity, as well as anyone can, I end up with infinity over infinity. I end up with this indeterminate form. And so if I apply L'Hopital's rule, remember that L'Hopital's rule says that this limit is going to be equal to the limit of the derivative of the top function, 6x plus 6, over the derivative of the bottom function, 4x. And this still gives me an indeterminate form, but we learned in our last lesson one of the properties of L'Hopital's rules that if I end up with an indeterminate form, I can just apply it again. And applying it a second time is going to give me the limit as x approaches infinity of 6 over 4, and that reduces to 3 halves. So this is one situation when I've got this infinite over infinite limit that I can use L'Hopital's rule to kind of evaluate it. The second time where I could use L'Hopital's rule is where I have this 0 times infinity. Of course, it seems to us that 0 times anything should be 0, infinity times anything should be without bound, and so the limit will be 0 or undefined or some value in between. So let's do a sample limit of this. The limit as x approaches infinity of 1 over x times the natural log of x. So I'm looking at this limit. I've got a product of two functions. As x goes to infinity, 1 over x goes to 0. And as x goes to infinity, natural log increases without bounds. So I end up with this 0 times infinity situation. And so notice that I can rewrite this as the limit as x approaches infinity of natural log x over x. And so what I've really got here is I've been able to rewrite this product as an infinity over infinity in indeterminate form. And that's one of the ways that you'll notice this can always be rewritten as either 0 over 0 or as infinity over infinity. You'll just have to manipulate it algebraically to get it look like one of those. So if I continue along this vein, because I have this indeterminate form, I can apply L'Hopital's rule. So I've got the limit as x approaches infinity of the derivative of my numerator divided by the derivative of my denominator. Now, this ends up being the limit as x increases without bound of 1 over x, which is 0. And so it ends up in this situation, the 0 truly does win out. And so my limit actually evaluates to 0. And one of the things that we should notice from here is that we really can't predict what the limit's going to be with any degree of accuracy. I could predict that the limit's always going to be 0 or always going to be infinite or always going to be 1, but in reality there's always some way to come up with coefficients or sums of functions that make it so that the values are non-trivial, not going to be just zeros or ones or infinites. And I wanted to do one last example of these three, this infinity minus infinity situation. So I want to take a look at the limit as x approaches 1 from the positive side of 1 over the natural log of x minus 1 over x minus 1. Now notice, as x approaches 1, the natural log of x will approach 0. And so that means the reciprocal will increase without bounds, since this is positive. And similarly, here if I substitute x equals 1, I end up with 1 minus 1, which approaches 0. And so the reciprocal would increase without bounds. So this is an infinite minus infinite situation. And as I usually do with a difference of two fractions, is I want to try and make it into one fraction. I want to look for that common denominator. So this should be equal to the limit as x approaches 1 from the positive side of x minus 1 over the natural log of x times x minus 1 minus natural log x over natural log x times x minus 1. Basically multiplying my denominators together and multiplying the numerator of 1 times that extra term. So I end up with the limit as x approaches 1 from the positive side of x minus 1 minus natural log x over the natural log of x times x minus 1. And so looking in this as x approaches 1 from the positive side, I've got a 0 over 0 situation, and L'Hopital works perfectly for these types of problems. So I'm going to take the derivative of the numerator. Derivative of the numerator would be 1 minus 0 minus 1 over x as x approaches 1 from the positive side. When I take the derivative of the denominator, though, this is the product of two functions, and I really need to evaluate this as a product rule. So it's going to be first times the derivative of the second plus the second times the derivative of the first. So what I've actually got here is I've got the limit as x approaches 1 from the positive side of 1 minus 1 over x over natural log x plus x minus 1 over x. And this looks pretty complicated, but if I were to multiply the top and bottom by x, that actually gets rid of all of my fractions. So I've got the limit as x approaches 1 from the positive side of x minus 1 over x ln x plus x minus 1. And again, I end up with this 0 over 0 indeterminate form. And so I can use L'Hopital's rule once more. So when I do that, I get the limit as x approaches 1 from the positive side of 1 over, here I need to treat this as a product. So this is going to be first times the derivative of the second plus the second times the derivative of the first plus the derivative of x minus 1, which is 1. so I end up with 1 over 1 plus 1 plus the natural log of x as x approaches 1 from the positive side. So I really have 1 over 1 plus 1 plus naught, which is 1/2. So again, notice I don't necessarily get 1 or 0 or infinity as an answer. I can get a peculiar answer of 1/2, even though there was no 2 in the original problem. So these are 3 of my indeterminate forms, but in fact, there are a whole lot of infinite indeterminate forms. I could have a situation of 1 to the infinite power, because 1 to any power should be 1, and anything to the infinite power should be infinite. So which is it? It's indeterminate. I could similarly look at infinity to the 0 power, or 0 to the 0 power. And all of these are indeterminate forms because each of these I could think of as a function where one term is dominant, or a function where another term is dominant, and get two contradictory answers. And I want to talk about this example here by doing a classic example, something that you may have learned in your pre-calculus class. So I want to talk about the limit as x increases without bounds of 1 plus 1 over x to the x power. Now, in this situation, I've got a variable expression raised to a variable power, and the way that we've dealt with this all year is through logarithms. So I'm going to say I'm going to let L be equal to this limit, and so the natural log of L would be the natural log of this limit. But because natural log is a continuous function, I can actually bring it inside and end up with the natural log of 1 plus 1 over x to the x power. And of course, what's the reason we do this is because we can bring the x completely outside of the logarithm. So I've got the limit as x approaches infinity of x times the natural log 1 plus 1 over x. And this is one of those situations where I've got infinity times 0, one of those indeterminate forms that we talked about before. And on the previous slide, we said what we do is we try and rewrite this as a fraction. So I get infinity over infinity, or 0 over 0. So I can do that by rewriting this x as 1 over x in the denominator, because dividing by a fraction means we multiply by the reciprocal. So I've got the natural log of 1 plus 1 over x in the numerator, and I've got a 0 over 0 situation when I try and substitute. So L'Hopital's is a wonderful approach here. So using L'Hopital's, I get the limit as x approaches infinity of 1 over my argument times the derivative of my argument. That's for the numerator. In the denominator, I get negative 1 over x squared as well. So I've got a common factor in the numerator and denominator, and I can divide that out. And so what I get is I get the limit as x approaches infinity of 1 over 1 plus 1 over x, and this is pretty straightforward to substitute. I get 1 over 1 plus 0, which is 1. The thing I need to keep in mind here, though, is that this is natural log of L, and I'm really trying to solve for L. So if the natural log of L is equal to 1, that means L would really have to be equal to e to the 1, or e. And Euler's constant, this is one of the ways that Euler's constant can be defined. And we saw this when we started thinking about our compound interest problems in our Algebra 2 and pre-calc classes. But what I'm doing is I'm letting the number of subdivisions increase without bound, and the time, the interest rate is being divided without bound. And we saw that this limit does give us the constant for exponential growth. So this is a classic example of one of the limits that we've solved, and we can do this using L'Hopital's rule. I talked about the other two indeterminate forms, and I want to try at least one of those here. So more fun with logarithms. By the way, all of these indeterminate forms, like 1 to the infinity, or infinity to the 0, or 0 to the 0, all of these involve using natural log to try and evaluate the logarithm, to try and evaluate the limit. So let's say that I'm looking at the limit as x approaches 0 from the positive of sine of 2x raised to the x power. And so I see, substituting 0, this is going to give me a 0 to the 0 situation. And so what I need to do is try and evaluate this. So I'm going to say L is equal to this limit, and the trick that we use is we said that the natural log of L would be equal to the natural log of this limit. So this is the limit as x approaches 0 from the positive side of x times the natural log of sine 2x. Basically, I'm taking the natural log, and then this x will pop in front. And this is a 0 times really negative infinity. But this is a 0 times infinity indeterminate form, and we said that we wanted to try and rewrite this as a fraction equals 0 over 0 or infinity over infinity. And in our previous example, what we did is we put the variable in the denominator, and that approach looks really good here as well. So I've got the natural log of sine 2x over 1 over x. And so what I've got is I've got negative infinity over infinity as my indeterminate form, and L'Hopital's rule applies here. So using L'Hopital's rule, the derivative of the denominator is negative 1 over x squared. The derivative of the numerator is going to be 1 over my argument times the derivative of my argument, and the chain rule happens. So I've got the limit as x approaches 0 from the positive side of this. Now this is a pretty convoluted function, so what I'm going to do here is I'm going to rewrite this. I've got cosine over sine, so this is really cotangent of 2x times 2. And this is really negative x to the negative 2 power that I have. The limit as x approaches 0 from the positive side. And what I can do is I can rewrite this as the limit as x approaches 0 from the positive side, having a negative exponent in the denominator is the same as having a positive exponent in the numerator, and having cotangent in the numerator is the same as having tangent in the denominator. So I really could look at this as being negative 2 times x squared over tan 2x. And I can see that this is a 0 over 0 indeterminate form. So I'm going to use L'Hopital's one last time here. So I've got the limit as x approaches 0 from the positive side. The derivative here would be negative 4x, and the derivative in the denominator would be secant squared 2x times 2. But at this point now, if I try and substitute, I get 0 in the numerator, but I end up getting 2 in the denominator, because cosine of 0 is 1. Cosine squared is 1. The reciprocal of 1 is 1. And 1 times 2 is 2. So this is not indeterminate forms, so I actually get 0 over 2, which is 0. And so what that means is that my actual limit is equal to 0. Well, not my actual limit. Remember, this is the natural log of my limit. So to find L, I need to take e to the 0 power, which ends up being 1. So this limit, as x approaches 0 from the positive side of sine of 2x to the x power, is equal to 1. What we've done here is we've taken a look at how L'Hopital can deal with other indeterminate forms, not just 0 over 0, but the other indeterminate forms we talked about, like infinity over infinity, or infinity minus infinity, or 0 times infinity. And all of these we either try and rewrite into the 0 over 0 or infinite over infinite. And the other indeterminate forms we talked about, the ones involving exponents. And whenever I see these exponents, I need to use natural log to try and simplify it. So it's the product of two functions rather than a function being raised to a function. So this is Mr. Potter. Thank you for watching. Have a great day.